All right, hello everyone. Welcome back for the ones that have seen my earlier talk, and welcome to everybody else, of course, as well. Great turnout, I'm really happy. Today I'm talking about a new approach about data processing, and in particular, processing data, stream data, and batch data in one model. A little bit about myself up front. I'm Robert Kubis. I'm a developer advocate for the Google Cloud Platform. And we understand our job as being a bidirectional job between you guys who build on top of our platform and the developers that build that platform within Google. So you find me on Twitter or on GitHub and other mediums, so please feel free to reach out. We always like to hear constructive feedback, things where you get stuck, where you think things can be made simpler, and I'm going to feed that back into the organization and try to make our products better. Now, today, I'm going to talk a little bit about the data processing history within Google and how we basically came to that approach to process streaming and batch in one model and how the environment looks like today. So we go back roughly to 2004. And if you see here, like this is kind of like a dimmed down data timeline of papers that we have published in that space. Now you see there's nothing before 2002, and Google is existing since 97. Now why is that? In the early days we were really scrambling and like keeping the company basically running and keeping up with the growth, so we didn't have much time to write papers and innovate in cool stuff that much. Now one of the big stones in data processing is definitely the publishing of a MapReduce paper. Now, I guess most of you already know what MapReduce is. I just want to very briefly touch it. Basically, what you do is you have a lot of data. You basically divide that data up, give that to some machines that run a mapping function on it, basically extracting a key. And then you shuffle around by that key and give basically these elements to so-called reducer machines. And these reducer machines do an aggregation on it, on that basically group, and then you write that out to somewhere. That's very simplified. Now this MapReduce algorithm or way of processing data is very, very powerful. You can pretty much put any data processing problem into this, but you might have to modify it beyond recognition. So it might be difficult to maintain or to further innovate on it. Now, MapReduce is great, and it took care of a lot of things like dealing with failure, dealing with distribution of the data between the steps and things like that, and you could scale it out very nicely because it's distributed processing. But it didn't handle things in between. So you had your data job, you run your MapReduce job, and then you have the data somewhere, and you might want to run another job on it. You had to move the data from A to B. You had to manage that lot of these things yourself. So what we really needed is a way to build pipelines, data processing pipelines. And there is where Bloom Java comes in, where we basically build a Java API around building these data processing pipelines. So it's a higher level API that makes it much more simpler to basically deal with input sources, processing, and then outputting, and that like in multiple steps. So it's basically cross transformations that you can do in a series of MapReduce jobs. Now, how does it look like in code? You basically read in your data. In this example, we want to calculate the average temperature in certain locations. And we have the location and temperature data in a database or in some kind of like data store. Now we read in this data into our P collection, which is basically a collection where we can do parallel processing on it. It's typed into the sensor event, and then we do a parallel pardo on that where we extract basically location. Then we group it by the location and doing a mean per this group key. And then we write that out to some kind of data sync. In this case, we write it out to Bigtable, for instance. Now, we taught everybody at Google, every Nuclear pretty much, how to use Bloom Java. And Google lives on basically processing a lot of data to provide you the most recent and best insights into any kind of data that's out there. And like if you do your searches, for instance, search for Krakow on Google, you get millions of results back in less than a second, right? So we have a lot of power in processing a lot of data. Now, our Nooglers basically started writing a lot of data jobs in Flume Java. And it's a lot of data. But there's kind of a problem with this in terms of at some point you collect this data continuously and you want to get a result at some point. So what you usually do is you chunk this data up in kind of by time or some other way and process it based on that. So here's an example. We have the data collected and we split it up by day. And then we take a chunk of data for a day and process that. Now, the problem of this way of processing data is basically latency. If I split up my data by day, I have to wait basically a day plus the time I need to process this data to get insight into that data. Another problem that we have is that we might split up things that belong together by these artificial boundaries that we are setting. If we set as boundaries of a day, like Tuesday, Wednesday, Thursday, if we have a 24-hour by 7 business which operates around the world, we are definitely splitting up things like sessions, for instance, where we might want to get insights in. So if we really look at that data, what we are getting, we're actually getting a continuous unbounded stream of data that we want to process. And we don't want to put like artificial boundaries to actually process this data. Another challenge in this is, especially also if we look at these artificial boundaries that we are setting and how we are processing is that data can be delayed. Imagine you have, for instance, a mobile game and you're collecting data from that mobile game, be it like some Bubble Crush candy game. And you go on a transatlantic flight, and once you step out of that flight, you turn on your Wi-Fi again, and all these information basically streams into your system for processing. Now, the time when these events happened during your flight versus the time when they are available to be processed in the system is different. So there is a delay in there. And if you don't take care of this delay, you might calculate incorrect results. So you have to somehow deal with that delay. So how do we deal with all that? And that's where Mealwheel comes in. So Mealwheel basically as a framework and tool set to calculate, do data processing on streaming. So basically, it's a framework for building low latency data processing applications. And it's a directed acyclic graph, which you write in there, and then the system manages everything for you in terms of like moving the data from A to B and things like that, and keeping state of the flow. Now, the processing patterns that you use in there is like what you pretty much are familiar with from other ways of processing data. One of the things, very simple, for instance, filtering element-wise. And then once you have filtered them, you basically still want to get like aggregations of your data. So you somehow have to define like what is the latency boundary that you want to set. Like what is the latency that you can accept, and what kind of like sizes of windows do you want to use to aggregate your data. So one thing you can use, for instance, time-based aggregation, what we see here. So basically put 1 hour windows and put all data in these 1 hour windows after we basically just stream through, and then we calculate aggregations on that. So I want to go a little bit a step back and want to look at like some use cases and want to use like 3 criteria that I look at for these use cases in terms of data processing trade-offs if you look at stream versus batch data processing. So one of the things that is really important in many cases is completeness. Are you calculating the correct results for the data that you have for your processing? The next thing that I already touched on is latency. Like when do you want to get results? And is it important to get them very immediate, or can you wait for these results? And the third one, which always is somehow important for your business, is like how much costs, how much money do you spend into these pipelines to either get like completeness or latency or both. So one of the examples is a billing pipeline. And I just want to point out one caveat in this graph. So on the lower axis, on the x-axis, you have like these three criteria that I just mentioned. And on the y-axis, you have the importancy. Now, what could trip someone off, and it tripped me off in the first time when I created that graph, is basically if the bar for low latency is low, it doesn't mean low latency. It means the low latency is not important. So important to point out here. So for a billing pipeline, of course, what is really important is completeness. You don't want to overcharge your customers because that gets you angry customers, and you don't want to undercharge your customers because that's not good for your business, right? So you want to really make sure that the billing pipeline that you have to calculate costs are correct. Now, latency might not be that more important. Your customer probably can wait like a day or two till they have like their final billing for the month. Now, low cost is also not important because you really want to have that correct. So you can actually spend some money to really have this billing correct, to not have unhappy customers or bad business. Now, in contrast to that is like a live cost estimate pipeline. For instance, for Google Cloud Platform, if you get one of our GCE instances, they calculate basically what your monthly running rate is, like what your bill probably will look like at the end of the month. So you get an estimate, and you want to have that estimate pretty like timely in terms of it should be accurate and not like from 3 days ago or something like that. So low latency here is actually important, and completeness somewhat. You don't want to be ballparks off from the actual bill at the end of the month. But you also don't want to spend a lot of money into this pipeline in terms of that it eats into your revenue. And last but not least, abuse detection pipeline. Now, for instance, this is really in terms of important to save money that you don't earn in your business in terms of preventing that users abusing your system. Now, there, completeness is not that important in terms of you want to be quick, rather quick to detect abuse, but you can have some false positives. In terms of low cost is not important. The more money you can actually spend on this pipeline, the better your abuse detection system gets, and the more money you can basically save by preventing somebody spending your money. Now, if you look at the state-of-the-art architecture for these use cases that we just saw, how to actually get the results out of your data processing pipelines, traditional, you actually looked at like a lambda architecture set up to get either like your really correct results with some more latency, or you get like your estimates in a more streaming kind of fashion system. So as you can see here, you're basically in a lambda architecture, you have your data stream, you save that in some database, and then for your billing, you run for instance, Spark or Hadoop to get your billing, and then you run like Flink or Spark streaming to get your approximates, for instance. Now, we didn't want, like, the challenge with this approach, if you look at it, is you have different systems that you have to maintain. Like you have like your Hadoop system at the top, for instance, and you need experts for that maintain the system, keep it running, and everything, right? And then you have your streaming pipeline system with Flink or Spark streaming or things like that, which also has to be kept running, and you also again need some experts. You need experts to program these pipelines, these different pipelines. So it's kind of different teams and different qualities of people that you need to maintain these both these systems. And at the end, you somehow need to reconcile the results that you get out of both of our systems. So it's rather complex and difficult, and actually you cannot really reuse a lot of the skills that you have in either of the systems. So that's where Dataflow comes in. So we basically built Dataflow inside Google to not make these sacrifices between correct and batch and estimate and streaming. We wanted to have one system where we can basically get both out of it. So where we can run streaming and batch processing, and you have like one programming model, like your developers will learn one programming model and they can write their pipelines in there, and they can either do batch or stream processing. We then donated this, and it became a top-level project in the Apache Foundation in the beginning of this year. So Dataflow is available now as Apache Beam, as an open source data processing API, which can not only run on Google Cloud Platform on our Dataflow service, it runs also on like Flink or Spark or other runners, Gearpump. So there's a whole ecosystem which is building right now where you can run your pipelines when you write them in Apache Beam. So now what I want to show, and I want to show that here if you want to participate, I have a little game where I write a pipeline, and I'm going to show you the pipeline with some coding later throughout my talk. But so basically what that game does, and I can show you, I get back to this QR code in a second. Basically it's a very simplistic game. You get a color assigned for a team that you're playing for, and then you basically have to hit the color that you're assigned to, and it's changing every 200 milliseconds. And then I'm calculating in the background with Dataflow and with Apache Beam model on top of Dataflow, I'm calculating your own hit success rate and your team's success rate. So basically, yeah, so that basically gets pipelined through a couple of systems under the Google Cloud platform into Dataflow, is then processed and then written out on the one hand back to you on your mobile phones, or also on our storage system where I write it to BigQuery. So here's the pipeline, as you can see. It's pushed to PubSub, then to Dataflow. It's always good to archive. And then I basically push it to also again back to PubSub so that you receive the results. Now, to get correct results with Apache Beam, we have to make a differentiation for the time that I mentioned already, the time when an event happens versus a time when the event is actually available for processing. So here in this example, we calculate team scores, and these have happened between 12 and 12:09, and we have the time when the event was actually happening on the x-axis, and on the y-axis we have the time when it's actually receiving in our system to be processed. Now, this dashed line that you see here is our real-time line. Now, if you find any events down here, please let me know after the talk. I can get you a good job. This basically means if you find anything in this part here that you can look into the future. So there's not possible that we have any events here. Now, here, if like our events are very close to this line, that basically means that the delay between the event has happened versus delay when the event is being processed is very low. Now, as we see like here, like the number 9, this event has happened around 12:01 and comes into our system around 12:08 for being processed. So there's a 7-minute delay for this event being processed. Now, how can we actually get the correct results of these data, of the continuous data, which might be sometimes delayed? And in Beam, we basically formulate around 4 questions that we are asking to get the right answers out of our data. These answers are basically what results are calculated. That is what you're used to from like Hadoop or MapReduce jobs. Like basically, what are the grouping that you're doing? What is the aggregation that you're doing? That's basically your calculations. The second question that we are asking is where in event time are results calculated? So we just saw this graph where I had the different events. Now, if I want to get like low latency results, I basically have to group them in some kind of small time windows. So I have to know basically where do I have to put this event. The next one is when in processing time our results are materialized. So that basically means when am I actually pushing results for my calculation downstream. So if I window them and do an aggregation, I might want to wait a little bit for late incoming data. So I have to make a decision when I'm actually materializing this data. And then the last one, how do I refine my results is basically looking at like what am I doing with the data when late data is coming in after I already materialized results, or what am I doing if I want to materialize results early, for instance. So what are computing? As mentioned, very familiar. We're doing like parallel processing on elements. We do aggregation or like a composite of it. Very straightforward. So this might look familiar for you if you have, like, again, this example of like calculating some means. In this case, we're calculating the scores for a team. We basically read some data into our P collection, as we saw from Java. And then we do parsing, extracting the key, and then we do the aggregation. So that is the what part of our pipeline. Now, if we do this without anything else that we write right now, we basically that's basically batch processing, right? So we have to wait till the end of our data set to calculate the entire sum in this case and emit the results. So we have to wait till 12 or 10 to actually materialize a result of 51. Now, there are different ways to window these events in Apache Beam. In our case, we're going to use a fixed window. We basically say, I want to have like per minute aggregation. But there are also other windows semantics that are supported, and you can even write your own if you like to. Some that are available is, for instance, a sliding window where you basically say, I have a 5-minute window and I shift this 5-minute window every minute, and I want to have an aggregation over this sliding window. Another one is sessions, where you, for instance, based on a user key, for instance, and some kind of delay, you can define like sessions for a user, and you do the windowing per like the user key, and you don't use time in this case. Now, for our example, when we ask the where question, where in event time do we want to put it, we use here in this case a fixed window of two minutes. So basically apply to my input of the data that I read into my P collection, I'm applying a window function, and I basically say, okay, I want to have that by event time, based on the event time, put into 2-minute windows, and then doing the aggregation. So how does that look? For this example, we basically have now these 2-minute boundaries here. But again, we don't have any semantics right now to emit results early. Only what we know right now is basically how did the team scores process over time in our batch. So we have basically every 2 minutes a team score, and so we know how it did process, but we again have to wait till the end of all the data was read and processed till we can emit some results. Now we want to get low latency results, right? So if you, for instance, search in Google for a team event, you want to know what is the recent score. You don't want to basically have all data. So you somehow have to find a way to get actually early results. And that's where the when question comes in. So when in processing time I'm actually emitting results. And here I need to go back to this differentiation between event and processing time. So basically, if you look in a real-world system, it's very rarely that you have a system where the data that is happening comes into your system to be processed right away when it's happening. So what could happen, for instance, is your system is overloaded, and so basically you have like some data building up, or as mentioned, like if somebody is offline or in a bad connection area, the data comes in late. So we need still to somehow figure out like when do we actually have seen all data to a certain time point in my event data. And that's where we use something called a watermark. So you have here basically the event time again, and the processing time, and the red line that you see is our watermark, where we believe that we have seen all the data up to a certain point for the event time. Right? And the wider this gap is, the larger is basically the delay of the data coming in. So now if I want to emit my results so that I basically believe that I have seen all my data for my window, let's assume this 2-minute window from 12 to 12:02, I might, like my watermark might tell me like 12:03, I believe like we have seen all your data. And that is based on heuristics, or if you want to implement it, you can also, like if you know really like when all your data has come in, you can also define this watermark for the system. Now here in my case, I basically trigger results after the watermark has passed. And now what we see is actually that we get like much faster and much lower latency results for our data processing system. So we still have these 2-minute windows, but now for the first window, as you can see, we are emitting a result for it already at 12:02. So we think we have all the data actually at the point we are passing the event time. And then we have like here, for instance, the second window, we wait a little bit longer after the window until we actually emit the results. Now, what we can also see here is that some of the elements have, or one of the elements has actually not been considered. So here we have this element that came in late into the system, and we have already emitted a result. So what we have to do here is actually we have to deal with this. And that is where the fourth question comes in, is how do refinements relate in this whole data processing? Now this is a lot of code here, and I go through it. So basically we have our window and we have our triggering. So now we refine our triggering. So one of the things is what we want to do, we have 2-minute windows, and I don't want to wait 2 minutes till I get like an estimate team score. So one of the things that I'm doing in here is I add early firings. So the early firings allow me to actually give an estimate result of my window before the window watermark has passed. So in this case, I'm using the processing time, so from the time the window has started, and then every time, like every minute basically, I'm emitting an estimate result. So this is for my estimates. Then the other one is late firings. So late firings basically are triggers that are triggered in the case of I have closed my windows, I have closed my windows, I have passed the watermark, I have triggered a result downstream. Now, if a data point comes in late, what am I doing this? So this basically says that I'm triggering this late firing trigger already at the point when one late element comes in. Now I can do things like, okay, I don't trigger every late element, I only trigger every 10 late elements. Or I only trigger like if a certain time has passed or things like that. Now, the other thing is, this keeps the window open, and if you keep that window open forever, you basically run out of memory. So at some point, you have to actually make a decision to discard that window. So this is the part of which we see here with allowed lateness, which basically says, like, how long do I keep that window open? How long do I allow late data to come in so that I still process it? And last but not least, you have to define what you're actually doing with the data. Are you emitting aggregate results? So do you do the entire calculation on the entire window again? Or are you only emitting differences? So in this case here, I have accumulating fired panes, which basically means I'm doing the aggregation on the entire window data again. But you can also use discard fired panes, which basically means I don't have to keep as much data around for keeping that window open. So now what we can see is basically we have here an on-time trigger and a late trigger for the first window. We trigger the result downstream 5 for the first window, and then the late element comes in and we trigger the element, the result 14. So we calculate the entire aggregate again. And as we can see in the second window here, that is actually open much longer. So here we basically emit every minute an early result. So we see the early result 7 and 14 for the second window till we actually pass the watermark and emit the on-time result. So what have we just seen, or what have we just gone through? We basically went with these 4 questions. So what am I calculating? Where in event time do I calculate? When do I actually emit results? And how do I deal with things like late data and if I want to get early estimated results? So by going through these 4 questions, we went from a batch system, from a batch processing system, to a stream processing system without losing correctness. So with this model, you basically can run your data processing pipelines and get still correct results even if you run them on streaming data. So I want to go over and show really quick like how that looks like in code for the little game that I just showed. So here in this example, I basically first do some housekeeping at the beginning. So I mentioned that the system uses PubSub as an input source, where all these events that when you click on your data are going to. So I'm basically using PubSub as an input. Up here is basically pipeline options that I'm setting in terms of where it's running and project and things like that. Then I'm reading the data from PubSub, and the first thing that I'm doing to my stream of data that I'm reading is I'm writing it to BigQuery. So this is my archival pipeline, basically. Now, the next thing in that demo, I'm showing you team stats and I'm showing you player stats. So this is basically what I'm calculating. And you see here, down here, so this is my team stats. So I'm calculating these team stats, and then I'm writing them to BigQuery, and I'm also writing them to PubSub. So both these things that you see here basically are writing my aggregates to PubSub and BigQuery. And I'm doing the same to my player stats. Now, if we look at the data, what I'm doing actually is, first, I'm extracting the team that you're playing for. Then I'm grouping it by the team. So very logical, the step that you would go to in your mind as well. So extracting by key, extracting the key, grouping by key, and then I'm doing a parallel aggregation. So here in my calculate team stats, I'm doing nothing else as like doing the aggregation and writing that back into a table row, which I'm using as a data format. So there's nothing special here. It's really very simplistic calculations. Now, this is basically, if I run this is basically a batch job, what I'm doing right now. Now, we went through the steps of what we have to do. So first is, where do I have? So basically, for that little game, I'm doing a fixed window of 5 minutes. So every 5 minutes, I want to calculate results over the 5 minutes. So next thing that I want to do is I want to do some triggering. And here, as basically, I want to trigger after the watermark. And because it expects a type, I have to basically give that a table row here. So then now we basically have no early results. We have no late refinement and things like that. So we still need to talk about the how. And that is basically where this comes in. So this I'm doing on the watermark trigger. I'm basically finding that trigger, the past end of window trigger, with an early firing here, as you can see, and a late firing. So early firing is basically every 10 seconds I want to calculate, I want to get an estimate which I send to you on the mobile phone or on the web page. And then if I close this window and I get another late arrival of a tab, I'm also firing the trigger or basically calculating the result for each element that is coming in late. And I'm keeping this window open for 10 minutes. So that's it. That's like all the pipeline that is there for this demo that I basically were running. Now, if I want to run this on Dataflow, I basically works with Maven. Let me put that up here. So we basically see, oh, of course. All right, nope. Sorry. Okay. So basically what we see here is a couple of arguments that I provide for this pipeline. But what you don't see is anything in terms of like installing software or setting up machines or anything. I'm only here in this case say like how many initial numbers of workers I want to have, but you can also define in terms of like auto scaling or things like that. So here I define basically that I have a streaming pipeline that I'm doing, and I have to find the zone where this is going to run in. And since I have this pipeline already running, I basically say that I want to update this pipeline so this job doesn't fail here. Now, if we go back to the web page, how does that look on a Google Cloud Platform? You basically have a pipeline here. Let me go to the streaming pipeline. So this is basically the one that is going to be set up right now. So we are starting the new pipeline and then switching over from the old one, basically. So here you can see the pipeline displayed in our Google Cloud Platform developer console, and you see all the elements that we are doing, like reading from PubSub, windowing, keying, aggregation, things like that. And you can also see like how many elements have been added and processed in the whole thing. Now, I mentioned that I'm writing all of this back to BigQuery. So one of the things that I want to do really quick is running a batch pipeline. So how does my batch pipeline actually looks like? So basically, if you look at the batch pipeline coming from what we have done before in terms of the streaming pipeline, you can see that I'm not doing anything in terms of like the refinements of triggers or things like that. I have exactly the same processing that you have seen earlier in the streaming pipeline here in the batch pipeline as well. Now I'm doing a little bit of windowing here in this case, so I want to explain this. But basically what I want to do here is I want to calculate sessions. So basically for this talk, I want to see like which team won in this talk. So I'm won in this talk in 30 minutes, so the past 30 minutes basically, and calculate for these 30 minutes windows in a batch processing pipeline, like who's winning. So that's why I have some windowing here, and I'm basically extracting here a timestamp out of my events that I have and use these timestamps to actually group by my event timestamps. Now if we go back to our pipeline, you basically see that this is started and it takes a while to run, so I'm going to go back to this after a while before I want to go to the slides. And please remind me if I forget. So here is what we do with the batch pipeline. We basically read from BigQuery the historic data that I'm always storing. I'm crunching it in Dataflow with Apache Beam, and then writing it back to BigQuery. Now, in terms of, I mentioned that Apache Beam pipelines can run on different runners. And the ones that are supported right now is like Fling, Spark, Apex, GearPump, and there are more in the pipeline. And of course, you can also run it on Google Cloud Dataflow. And you see here, and you find that on the beam.apache.org webpage, the compatibility in terms of the features that are supported by the SDK and by the model, by the Apache Beam model, versus like what is supported on the runner. But it enables you basically to write and run Dataflow pipelines or Apache Beam pipelines on-premise and move them over if you need to grow into a public cloud. So with this, I thank you very much, but let's see if my job finished. Still running. I can show you really quick how that looks like. So let's do a calculation on all time. This is our BigQuery tool, which is basically a tool that allows you to crunch a lot of data, relational data. It's a distributed database behind the scene. It's basically a data warehouse solution, and you can run petabytes run through petabytes of data in minutes. Did it succeed? Still running. So I just also want to point out here, which I mentioned briefly already, is that if you run these pipelines on Google Cloud Platform, everything else in terms of like management for the systems is taken care of for you. So we update the systems behind the scenes. We set all the parameters so that your Dataflow jobs are running very efficiently and that they are getting faster and faster every time. So basically, really what you can do is concentrate on writing your pipelines and concentrating on getting insights out of your data instead of dealing with the management and the hardware behind the scenes. So unfortunately, it is still running demo. And I really want to know like who's the winner in this competition here. Let's see, like probably yellow, as we can see here. It's assumedly yellow that won this team challenge for this talk. So let's give it another try if it's finished now. Still running. All right. With that, I open up for questions and we'll come back to it later. Anybody with questions? Did I put everyone to sleep? There's a light chuckle, so no. I have a question over here. Yeah. Yeah. So the question was based on data privacy if you put data into the cloud. Now, Google doesn't touch your data, first thing. Second thing, your data in the cloud is encrypted on rest and in transit as well. So between our systems, if your data is in flight, or between our data center, your data is encrypted. Also, if you look at BigQuery or Spanner or any other kind of storage systems that we have, your data is encrypted on rest. And there are also some products which allow you to come with your own keys so that you basically encrypt them and give us like the key that is only held in memory to process the data. Let's see if that finished now. All right, still running. That's a bad day. Any other questions? Otherwise, thank you very much for your attention.